Okay, just before I begin, I'm going to be talking for about 1 minute about death and violence. So if you don't want to hear about that, you can come back in 2 minutes, after which I will switch to the main topic of the talk. For the most part, I'm talking about processing large JSON files without running out of memory. My name is Itamar Turner-Trauring. This is based in part about some articles I've written about processing data in a more memory efficient way, making them faster, which you can find on my website, pythonspeed.com. So before I begin talking about how to make your software faster, it is worth pointing out there's software you shouldn't be writing about at all. Shouldn't be writing at all. So I grew up in Israel. My name's Itamar, it's a common Israeli name. So I figured I'd give an example from there. So the past 20 or so months, Israel has killed 52,000 people, of which about 15,000 are children. And a lot of this was from dropping bombs on Gaza. And the issue of that is they had to have a constant stream of these targets in order to sustain this level of bombing. And so they turned to AI models. So there's some models they got from Microsoft and OpenAI. And there's some locally developed models. They had a known error rate of 10%. So just their own testing suggested 10% of the time it was just wrong. So the error rate may actually be higher. And the way they made sure that the bombs actually landed on the person they were targeting is they would target them at home when they were home with their family, and so that increased the casualty rate by a lot. I do recommend the 972 magazine article. It has a very in-depth look at the organizational dynamics. So this is an extreme example of software you shouldn't be writing. Like most of you are, one assumes, not involved in anything that involves war crimes. But it's an example of a much broader issue, which is software can just amplify the harm that you can do. Anything a computer can do, you can do. You can simulate a computer with pencil and paper. You can run software in your head. If you're trying to debug something, you might do that. So computers and software don't let you do anything new, really. What they do is they amplify, let you run tasks vastly faster, let you run tasks at scale, assuming you've optimized your software appropriately. So if your software is hurting people, hurting the environment, then by making it faster, making it more efficient, you're just amplifying that harm. You're just making that harm that much worse. So the first question you should be asking yourself when it comes to optimizing software is, first, does this software need to exist at all? Is this software harmful? And if it is harmful, then you shouldn't be trying to make it more efficient. You should be trying to maybe find a different job where your actions won't be causing harm. So for the rest of the talk, I'm just going to assume that you've already gone through this. We can focus on actually making your software more efficient. So the specific problem I'm going to be talking about today is high memory usage when loading JSON. And it's really best to think of it in terms of multipliers. So I'm going to be using an example JSON file that I generated. It's a list of JSON objects, dictionaries. And the Python standard library, the file is 50 megabytes. And the Python standard library has a JSON module, so we import that, we open the file, we parse the JSON, and then we can iterate over this list, and we get dictionaries, and we can look up different fields in the dictionary and do whatever it is we need to do. And what we're going to do with the data, to some extent, doesn't matter, depending on, at some points in the talk it might matter, but in general, we're doing something with the JSON. Our focus on just loading the data. And so if you measure peak memory usage after you run this code, it's going to be 200 megabytes of memory used. And the file was 50 megabytes. So we've gone from 50 megabytes of JSON on disk to 200 megabytes of data in memory. So that's 4 times as much. And I measured it using user bin time, and I'll talk about measurement in a bit. So to some extent, you can say, okay, so just, 200 megabytes, like in this day and age, who cares about 200 megabytes? And that's reasonable. The issue is we're talking about a multiplier here. So now imagine that your file is 10 gigabytes. So if the multiplier is 4, you're going from 10 gigabytes on disk to 40 gigabytes in memory. And it's pretty common to have computers only have 16 gigabytes of RAM, where you're going to want to store your data in memory. And probably you're running some other programs, so maybe you have less than 16 gigabytes available. And so now you're trying to put 40 gigabytes of memory into 12 gigabytes of RAM, and it doesn't really fit. So at that point, the operating system will either start shoving data down to disk, which, if you have to do this rapidly, will really slow down your program because disk just isn't as fast as RAM, or your operating system will say, you're trying to load 40 gigabytes of data, you only have 12 available, this is not going to work, I'm going to kill your process. And so now, your program is dead, and your program is dead, you're never going to get a result, and next time you run it, you'll get the same result. So, having too much memory may mean that your program never finishes. So it's now infinitely slow. And to zoom in a bit, to focus a bit on the specific problem, the issue is peak memory usage. So here we saw, if you load 10 gigabytes of JSON, we expect peak memory usage of 40 gigabytes at least. If the average is 10 gigabyte, that doesn't matter, because even if like for the whole lifetime of your program, it's 10 gigabytes, and then for 1 millisecond or like 10 microseconds, it jumps up to trying to load 40 gigabytes, at that point, the operating system may say, sorry, this is too much, this is not like, you're gonna take the system down, I'm gonna kill you before things get worse. And so it doesn't matter that if you optimize the average to be 8 instead of 10, it doesn't matter if you still have a peak of 40 gigabyte. So that means is when you're measuring memory usage, you need to measure memory usage at peak. And there are a bunch of tools to do this. User bin time on Linux. If you pass a verbose flag, verbose flag minus v, one of the things it'll tell you is maximum residence size, set size. This is not the same as the time command in your shell. You have to do user bin time. The resource module in Python gives you essentially the same information using the same operating system facilities. Tracemalloc in the Python standard library tells you which objects are in your process, so it's like gives you more information. It's not just a full process, but it won't get all the memory from third-party extensions. And then there's a variety of memory profilers. I wrote 2 of them. Memory is from Bloomberg, and they will all not only tell you peak memory usage, they also tell you where that memory was allocated, so you can like actually track down the code that was responsible. In this particular case, since we're not, it's just going to be a reloaded JSON. We know what the problem is, so the profiler isn't necessarily as useful, but in general, the profile is a really great way to get this information. So you're loading some JSON. It's using way too much memory. What are you going to do? So we're going to cover 4 solutions. Buying more RAM, which is a combination of spending money and hardware, and then 3 solutions that involve software changes, so using a more efficient in-memory representation, only loading the subset of the data that you actually need, and streaming your data. So we'll start with buying more RAM. So one way to deal with the fact that you have to load 40 gigabytes of data is to make sure your computer has more than 40 gigabytes of RAM. RAM is the part of your computer where your running process stores its data if it's possible. It can use disk, but RAM is much faster. It's also more expensive, so you'll have less of it. So like this laptop's 32 gigabytes of RAM, 1 gigabyte disk. So you get a sense of the ratios. So you need to add more RAM. You can do that by adding more RAM to your computer. So I'm pretty sure I can upgrade this laptop. On Macs, this is harder, or I think maybe impossible. Most Macs have the amount of RAM fixed when you buy it, and you can't do anything about it. Some PC laptops have started copying this, and like they solder the RAM on, and you can upgrade it. And even so, if you buy a new PC laptop, you should make sure the RAM isn't soldered on, unless you know it's at the maximum and you couldn't buy more. You can buy a new computer or a used one. This is a refurbished computer, so it's a bit cheaper, more environmentally friendly. Buy a new computer with more RAM. Or you can rent a virtual machine in the cloud with lots of RAM. You can go as high as 32 terabytes. It's kind of amazing. And this will cost you a lot per minute, but if you're only running the job for 10 minutes every once in a while, that might be the easiest solution. The solution of throwing money at the problem is not always possible. Even if it is theoretically possible to buy enough RAM or rent enough RAM so you can process the data, you may need to scale. Like maybe you're running this code on hundreds of computers in the cloud, and so if you double your RAM requirements, you're doubling your costs, or adding 50% of your costs, and add hundreds of computers, that starts adding up, and you want to be able to run this without spending huge amounts of money. You may not control the runtime environments. Maybe you're writing some application or library that you're distributing to the world, and you can tell people, hey, you need to buy more RAM, but if it's too much, they might not use your software. And so you want to be considerate of your users, or make sure you can acquire customers more easily. Or you may not be able to predict the size of the data. If you don't know in advance how much data you're loading, then it's difficult to say how much hardware you need, like how much RAM you need to buy. And so in all these cases, buying more RAM is not a solution. And so next we'll switch to solutions that involve software. And the first solution is a more efficient in-memory representation. So we saw that when we loaded a 50 megabyte file with Python's built-in JSON module, that uses 200 megabytes of memory. So it's a 4-time ratio between the size on disk and the size in memory. So the question is, why is that? Like, where's all this memory usage coming from? And some parts of it are just people not paying attention, and so by mistake, they write a little bit of code that keeps some memory alive for longer than it should be alive, or they do some extra copying when if they did a little bit more work, they can make it more efficient. And so these sort of problems, while they do exist and they will impact you, they are also solvable. So you can go and file a bug against a library you use and say, hey, this is using way more memory than I expected, or submit a pull request with a fix. If it's open source library, and if you're lucky, it'll get fixed, and then your memory usage is down. These are not like sort of necessarily very difficult to solve if someone's actually focusing on it. But there's some more difficult issues. So when you load a JSON file into Python, you're creating lots and lots and lots of Python objects, dictionaries and lists and integers and floats and strings. And Python objects, for very good reason, have memory overhead. So consider, you can measure them with sys.getSizeOf, which is a built-in to the Python standard library. So consider the number 6,752. If you write that in a JSON document, that's going to be about it's going to be 4 characters, 6752. There might be a comma, there might be a space. So it's between 4 and 6 bytes on disk. If you load that into a compiled language like Rust, that might be a 8 bytes, so a 64-bit integer or 64-bit float. And so, you're using maybe 50%, twice as much memory. If you load it into Python, you'll be using more like 24 or 28 bytes per integer or float. And on a small scale, this really doesn't matter. Like, no one cares how much, if you have 3 integers and you're using 10 more bytes, who cares? If you're loading tens of millions of integers, though, it starts adding up, because now you're using 5 times as much memory as what was on disk. An empty Python dictionary is 64 bytes. Lists, I forget how much it was, but all these objects just have this overhead. And if you have a few objects, this really doesn't matter, and there's very good reasons why Python does this. But at scale, if you're loading millions and millions of objects, all this overhead adds up, and now you're using a lot of memory. And this is difficult to fix, because it's tied to fundamentals of how the Python interpreter works. So if the memory representation we're using is just adding a lot of overhead, what can we do to use less memory? Maybe we could switch to a different representation. And so one alternative is arrow, depending on the shape of your data. So arrow is a data format for columns of data. So the kind of things you would process with pandas or polars or a spreadsheet. So you have columns of data, and it knows what type the column is. So it knows this is an integer, and so it tends to store it much more efficiently than Python objects. And one way you can load JSON is with a library called awkward array. It'll create an arrow container. And one nice thing about arrow is you can pass it between different libraries that use arrow without copying the data. So you can take that arrow that you've loaded and pass it to pandas or polars, and then process it in pandas or polars, and then you just have to use awkward array to load the JSON. So here's some code. We import the library, we open the file, and then we say from JSON, and then you have an array. And I'm not going to show you how to move it to pandas or polars, but it is possible. If you do this, the peak memory is 100 megabytes. So now we've gone from 200 megabytes, or 4 times our file size, just twice the file size. So we've cut our memory requirements in half. It's pretty good. It has a downside, though. Previously, we had dictionaries and lists and integers and floats that were just normal Python objects. And so we can just interact with them. And now we're switching to, let's say, pandas data frame or polars data frame. There's a fundamental, or even the awkward arrays. And so now there's a fundamentally different API for interacting with your data. It may be a good API for interacting with the data, but it's different. You've been forced to change your paradigm of programming just because you want to be more memory efficient. And this may or may not be acceptable. So at this point, you might be thinking, why didn't you just load it in pandas or load it in polars? And the reason is because that doesn't actually help. It makes things worse. In both cases, they use even more memory than the built-in JSON module. This is, I expect, fixable if someone were to look at it, but out of the box, you don't want to load, at least JSON as structured the way I was looking at in these libraries in the version I tested, because it uses a lot more memory, not less. So that was solution number 2, which was changing the in-memory representation. And as we saw, that has the cost of you have to change the paradigm of interacting with your objects. Another solution is only loading a subset of the data you actually need, which sometimes is a solution that's available to you, sometimes not. So our data is a list of JSON objects, JSON dictionaries, and each dictionary looks like this. It's got an ID and a first name and a last name, and a description and a timestamp when it was created. And imagine that we only want to use 2 fields in our data processing. We only want to look at ID and created at. Like we're going to create some sort of visualization of when these events were created. We don't care about the names and description. So what we've been doing is we've been loading all the data, and then we're just ignoring the names and all the names and all the descriptions, not doing anything with them, and they're just sitting there wasting memory and like making it harder for us to load large files. So can we parse the JSON, but just not load the data we don't care about? And that's what we're going to try to do. So one way you can do this is with a library called the message spec. It's a serialization and validation library. It supports JSON, some other data formats, and what you do is you create a schema, and then once you have a schema, you can say load this JSON using the schema, and any fields in a dictionary that don't match that schema, it just won't bother loading into memory. There are slides available, by the way, so I'm going to link to it at the end. So you don't have to take photos if you don't want to. So here, in this case, we have a record, which has an ID, which is a string, and created at, which is a float, which are the 2 fields we actually care about. And then we open the file, we read it into memory, and this is an annoying thing where you have to actually read the whole file into memory because the API this library provides doesn't actually take file objects. So the first thing we're doing is we're creating a whole copy of the whole file in memory. This is unfortunate, but in this case, it's still worth it. This is why I opened the file as a binary file, because that makes sure we're not using extra memory. For Unicode, for regular Python strings, in some cases, loading them from disk might increase their size as much as 4-fold. So if you can, in these situations, you want to read it as bytes. Then we use the message spec.json.decode to say here is the string with some byte string that has some JSON in it, and the type is a list of records. So using Python typing syntax, and we're telling it this JSON document schema is a list of the records. The records are a thing we defined in this previous slide. And we get back a list of record objects. This is 100 megabytes peak memory, and half of it is just reading the file into memory. So we're still doing better than our original 200 megabytes. Our multiplier is 2 instead of 4. So that's an improvement. And this is, compared to our original code, a slight difference. Previously, we had a list of dictionaries. Now we have a list of record objects. So we have actually had to change a little bit how we interact with the data. On the plus side, this isn't a very significant difference. Like, it's still a list of Python objects. It really isn't that different. We're not completely changing paradigms as we did when we switched to something like pandas or polars. Again, you might be asking, why not use Pedantic? Pedantic does basically the same thing, except it uses way more memory when you load the data. Again, this should be fixable. I may have also did something wrong, used the wrong API. I'll get back to this at the end of the talk. So we've seen that one solution is changing the in-memory representation. We've seen that one solution is only loading the data you actually care about and not even bothering loading the data you don't. And a fourth solution and a third software solution is streaming or batching or chunking or incremental processing. These are all basically the same thing with different names. Depending on context, different people will use different names. And so up until now, we've loaded the whole JSON document. And maybe we dropped a few fields in every record. Maybe only loaded ID and created that. But we loaded the first and the second and the third and the 7,000th and the 2 millionth and the last. All of those JSON dictionaries got loaded at the same time into a list. And that uses a bunch of memory. But what if we only loaded them in batches? Or maybe if you loaded 10 at a time or 1 at a time, and then we process them 1 at a time or process them 10 at a time. And then when we're done processing them, we let go of them, and the memory gets freed, and then we load another 10. So we only have like a few of these records in memory at a time instead of all of them in memory at a time. And that'll save us a lot of memory. This isn't always going to work. There are some requirements. First, your JSON document has to have some concept of chunks of data that you can stream. If you imagine a JSON dictionary where each key has an arbitrary depth of other nested dictionaries, maybe the first key value is 1 million nested dictionaries, and the next one is 2. And so the chunks aren't really the same size, and like there's no way to predict how much memory they're going to use, and it's not even clear if it semantically makes any sense. So in some structures, this won't work. We're using a list of JSON dictionaries, so it's pretty clear what loading records in batches means. We load a few dictionaries at a time. In some structures, they won't work. The other requirement is on the way you're processing your data. Can you process your data in such a way that you don't have to have all the data available at the same time in memory? And for some applications, this will be a problem because you're going to have to, when you load the third item, it's going to have some reference to the 7 millionth item, and you need to have it in memory to do the processing. So you need everything in memory at once because you can't predict what you're going to need. But if you only are processing records 1 at a time, and that works, which is pretty common, then you can use this technique. So we're going to be doing this with a library called iJSON. The I is short for incremental, I believe, or iterative? Maybe iterative. And our data format is a list of dictionaries. So we import the library, open the file, and then we say for every record in iJSON.items, we pass it the file it's going to read from, and we pass the string item. And so what's going on here is iJSON has a little query language where we tell it which things it's going to parse for us. And the string item means every item in this list, parse it to us and give us a thing that lets us iterate over them. And so we're going to get an iterator over dictionaries. So record is going to be a dictionary, and then we can get fields, and we can do our processing. So it's just another for loop. Each record, like we get a series of dictionaries, and we can do whatever we want with them. Peak memory usage is effectively nothing. It's about 1 megabyte. It is unrelated to the size of the file. It would be 1 megabyte if this was a 10 gigabyte file. It would be 1 megabyte if this was a 100 gigabyte file. It's 1 megabyte for the 50 megabyte file that we're loading. That's because we're never loading the whole file into memory. We're just loading just enough to get the next dictionary, or maybe the batch of dictionary internally. And then it gets parsed, hands it to us, we process it, we drop it on the floor, we move on to the next dictionary. So we only ever have very little bit of memory that we're processing at any given time, and it doesn't matter how large a file it is. It may be that we then process this in some way that accumulates memory that's tied to the size of the document. But that's our own code. Just parsing the JSON effectively doesn't use any memory. It's just nothing. So it's a big improvement. We went from 4x to basically 0x. Now you might be wondering, how is this different than the code we originally wrote with the JSON module? Like, we opened the file, we parsed it, we iterated over it. How is that different? And so the difference is, and this is the old code that we originally wrote, when we do JSON.load, we get a list of dictionaries, right? So that means all of the data is in memory at the same time. We can access the first one and the second one. We can access the last one. We can access the 7 millionth one. It doesn't really matter. It's all in memory. It's all there. It so happens that we're going to iterate over it and do it one by one, and we don't actually need to have access to all of them at once. And if that's the case, if we're just going to iterate over it, there's no point in getting a list. An iterator is good enough. With an iterator, we can't get the 7th item or the millionth item or the last item. All we can do is say, give me the next one and the next one and the next one. But if all we're doing is a for loop, that's fine, and this is a really vast reduction in memory usage. Another question you might have is, how is this different than the previous solution we saw, subsetting, loading a subset of the data? And the difference is, previously we were effectively loading all the records into memory, but for each record we loaded fewer fields because we didn't care about some of the fields. In this case, with streaming, we are loading all the fields, but we're doing one record at a time. So that we're operating on the level, we're saving memory on the level of records. We're only loading records one by one instead of all the records. And so two different ways of saving memory, and in theory, you can actually use both these techniques at once if you happen to have a library that gives you the right APIs or hooks. In practice, for our use case, iJSON is probably sufficient because the memory usage is basically 0. So saving a tiny bit more memory isn't worth your time. But in other contexts, these techniques are more general, and you can apply them together. So some final thoughts beyond what we've covered so far. First, JSON is not a great data format. It's not really designed for streaming, and so you need a specialized library like iJSON. If you happen to be in some other programming language, it's not Python, maybe there is no parser like this. Maybe you can't read it in a streaming sort of way. You have a limited set of data types. If you want to encode a timestamp, there's no way to do that without higher level abstractions like JSON schema. Not as efficient to read as binary formats. So there's alternatives that might work depending on the shape of your data. So the shape of data that I was using in this example fits very well in, for example, columnar data like Parquet, which would be way faster to load and would also be less space on disk. Another alternative is new line delimited JSON, which I will go into briefly just because it's very relevant to our particular interest. There are multiple variants of this with lots of different names: LDJSON, NDJSON, JSON Lines, there's an RFC. They're all very slightly different, but they're all essentially the same thing. Like, it's not really fundamentally different. And the idea is, when we look at if we were to look at the kind of file we just started with, it's a list of JSON objects. So it's one big JSON document. We have a square bracket to open it, and then we have a dictionary, and then we have a comma, and then we have another dictionary, and then we have a comma, another dictionary, and then we have a closing square bracket. And it's one big JSON document, and if you use a normal JSON parser, you just parse the whole thing at once. So what we can do is we can say we are going to convert this into lots and lots and lots of JSON documents. Each JSON document is going to fit on one line of this text file. Notice there's no commas, there's no opening square bracket, there's no closing square bracket. Each of these lines is an independent JSON document. And then we just load the JSON document from each line separately. And this means we can do streaming much more simply. In particular, we can use any JSON parser we want. We can, for example, use the built-in JSON library. We open the file, we iterate over the lines, and then for each line, we just parse it as a standalone JSON document. Because instead of the file being one giant JSON document, it's one JSON document per line. We can have millions, billions, it doesn't matter. We're parsing each one individually. And that can save us a lot of memory. The second thought is that it is really, really important that you actually measure memory usage. So polars and pandas both use way more memory than awkward array. Polars uses arrows out of the box. Pandas, it's optional, and it's not clear to me to what extent. I had some problems loading the JSON file, and maybe with more work I could have done it in the arrow mode. But polars very definitely uses the same memory representation as awkward array, and yet use more memory when loading the data. Pedantic has a schema system. It has the concept of loading only part of the data, and yet use way more memory than messagespec. And so the issue is that memory usage is a thing that's very easy to miss. Like, slow software is more noticeable. It's easier to measure. People tend to prioritize it more. Whereas high memory usage, maybe you didn't even conceive of someone trying to load a 10 gigabyte file with your library. Or maybe it's just hard to measure. And also, it's very non-linear in its performance impacts. It's my code works fine, my code works fine, my code works fine, then my file gets slightly bigger, and now my process is dead because Linux killed it, or macOS killed it. And so it just tends to get less attention. And so you can't assume that just because this library seems like it'll use less memory, well, you actually have to measure it. So to recap, if you have high memory usage, there are 4 approaches you can take: spending more money on hardware, you can buy or rent, you can use a more efficient in-memory representation, you can load only a subset of data you care about, you can stream your data, or batching or chunking. And that is my talk. I have plenty of articles on my website about writing faster and more memory efficient data with a focus on data science and data processing in general. The slides are available on my website as well. I do consulting, so I can make Python software more efficient, and I've also do some open source maintenance, and I'm also working on a book on learning how to write fast compiled code from the perspective of a Python developer. Thank you very much, and I will be outside if anyone wants to talk.